wonderful workshop and giving me this great opportunity. In this talk, I will discuss that an ensemble of black hole solutions with a probability distribution can give more integrable physics beyond quantum chaos of the random matrix theory. First, let me explain my motivation. Fluctuations around the ADS single black hole configuration give rise to effective dynamics emergent from strongly coupled conformal field theories. If you consider quantum gravity corrections for this black hole solution, I mean, for example, wormhole configurations, for the spectral form factor, you will obtain the behavior of quantum chaos. I mean, T-linear increasing ramp and T-linear independent flat in the spectral form factor. Here, such quantum gravity corrections take into account the so-called level repulsion effect responsible for the Wigner-Dyson level statistics and consistent with the random matrix theory. In this talk, we will consider an ensemble of black hole configurations with a probability distribution where the probability distribution is determined self-consistently. As a result, we find a novel fixed point which does not show the quantum chaos behavior, referred to as an infinite randomness fixed point, characterized by a power law distribution function. You may consider three phases in strongly correlated disordered systems. When the strengths of disorders are less than their critical values, it is natural to expect a deceive metallic state. This phase shows the Wigner-Dyson level statistics consistent with the random matrix theory. When the strengths of disorders are above their critical values, it is natural to consider an Anderson insulating phase. It shows the Poisson distribution for the level statistics regards to be opposite from chaos and integrable. One may consider the current critical point of the metal insulated transition, which does not show neither the Wigner-Dyson nor the Poisson. Various one-dimensional conformal field series show RG flows in the presence of disordered effects, such as the random change in fractions and the random magnetic fields towards an infinite randomness fixed point. Here, the infinite randomness fixed point means that even if we start from a Gaussian distribution function for the randomness distribution, there is an algebraic flow to a power distribution function where the variance of such randomness is infinite. This is a disordered quantum critical state, neither a metallic or nor an insulating phase. This is a quantity average free energy in the path integral formulation. Here, C is an electron field in the Lagrangian, where GA are their effective interactions. Here, A runs from 1 to some n, whatever. It depends on the interaction channels. VA are disorder strengths. Also, you can consider various disorders. This F is the free energy at a given disorder configuration of disorders before averaging at UV. Then we perform averaging for all realizations of disorder configurations with the given UV probability distribution for randomness, like this. This is given, for example, Gaussian. Now we apply the Wilsonian algebraic transformation to this problem. In particular, we reformulate the Wilsonian algebraic transformation in a way to manifest the algebraic flows of all the coupling functions and random potentials in the level of the effective action. As a result, we obtain an effective holographic dual field theory where the algebraic scale appears as an emergent extra-dimensional space-time for the bulk effective action. For the time being, let's focus on the second equation here. This is a renormalized free energy function for a given disorder configuration. So, sorry, at UV here. Yeah. This delta function shows the algebraic flow for the random potential and coupling functions in the presence of such normalization effect of random potentials. Here, the determinant is nothing but the Jacobian factor to guarantee the of procedure. In other words, if you integrate out this sector, you obtain just 1. And also, if you integrate out this 1, it's just 1. This is an effective potential, the essential ingredient for this construction, which occurs from integration of quantum fluctuations, high energy modes in the RG transformation. And G, accordingly, at given n scale here, G is the RG scale. Now, the resulting Lagrangian here is given by fully renormalized coupling functions in the presence of the renormalized random potentials. Beta is the RG beta function are given by variations of the effective potential with respect to the disorder and coupling functions at a given RG scale, like this one. So, this effective action manifests the RG flow of the coupling functions. Yeah. It is straightforward to exponentiate these RG flows and construct an effective action with an RG scale G. Here, phi BA and phi J is a Lagrange multiplier field to contain, to describe the RG flow of the disorder potential or random potential and coupling functions in the presence of the random potential. Each Jacobian factor of the determinant can be introduced into the effective action via the so-called of force field here and here. Yeah, like this one. Again, free effective is the effective potential from the Wilsonian RG transformation. All these renormalized coupling functions and disorder potentials appear in the resulting higher renormalized effective Lagrangian, which gives the IR boundary condition. So this bulk RG flow has to fit this effective IR boundary Lagrangian. So everything should be determined in this expression in a self-consistent way. As you can see, the flows manifest the level of an action with an interaction of the emergent extra dimension C. We claim that this is an emergent holographic field effective field theory. Here, emergent means that the explicit manifestation of the ID flows in the level of an effective action, and holography indicates appearance of the extra dimension through ID transformation. Dual means that the bulk effective action is written in terms of the coupling functions and holographic fields, which play the role of order parameter fields given by a composite of the original electron fields. Two remarks are as follows. If you are familiar with the supersymmetric formulation of the Lagrangian, sorry. Okay. You are familiar with the supersymmetric reformulation of the line-giving dynamics done by Parisi and his colleagues long time ago. More people. This Wilsonian RG formulation is quite similar to the supersymmetric reformulation, except for the existence of this effective potential. Recently, this issue has been revisited by many other people, Rangamani and his co-authors, and Hong Yu and his collaborators, and more people, where two types of BRS symmetries are promoted into n equal to supersymmetries. Although I will not discuss in detail, let me just briefly explain my speculation. Anyway, based on these symmetries, one may obtain the corresponding word identities for correlation functions, which reproduce generalized fluctuation displacement theorems. I believe that the ID flows here should have such similar word identities, but the presence of the effective potential should play the role of an entropy production mechanism, I mean work. As a result, I'm expecting a new formulation or somewhat different understanding of the monotonicity of the ID flow expected to be analogous to the C theorem. This is an ongoing work. The other comment is about the promotion of the coupling functions into the dynamical coupling fields. So here, This is just the Lagrange multiplier field. There's no dynamics for this one. Just classical equation motion. That's Langevin equation. So the question is how to promote to the dynamical fields. It analogs to the typical deformation in the UV Lagrangian, where random fluctuation of coupling functions are introduced. See, here I'm considering a gross Levy-time model for chiral symmetric breaking and introducing random fluctuations of all the couplings. P is chiral symmetric breaking fields. So from this average mean value for this all the coupling, so wave function renormalization, velocity normalization, and chiral symmetric breaking, you can consider its average value. You can consider some random, some Gaussian fluctuation around that. If you integrate out these fluctuations, you obtain a TT body formed like effective Lagrangian. Applying the Wilson and algae transformation, you have now this pi square term. So this is the interactions. So the main point is all the couplings you have some new here. So essentially similar structure with this algae transformation. This shows that these coupling functions are promoted to be dynamical in the mathematical representation. As you can see, these coupling functions play the role of emergent metric tensors. You may imagine this is quite analogous to the ABM Hamiltonian formulation of the general relativity. The remaining thing not discussed until now is how to rewrite the distribution function given by original UV degree freedom in terms of IR renormalized ones of the resulting IR boundary effective field theory. The initial free energy in terms of renormalized coupling functions and disorder potentials has to be constant averaged by renormalized distribution functions in terms of all the renormalized fields. I mean, this is normalized one, and now I want to rewrite this distribution function in terms of originally it is written by UV degree of freedom. Now I want to rewrite in terms of fully normalized thing and disorder potentials. Since the initial pressure itself is invariant under the algae transformation, it gives Carlan equation for the free energy for the given realization of disorder configuration. The quenched averaging has to be also invariant as follows. As a result, the renormalized quenched averaged free energy remains invariant under the algae transformation. Then we find this equation here. So if you change the algae transformation, it's promoted here and here. It should be invariant, and this is invariant, and this part is invariant, and this is invariant under the algae transformation. It is straightforward to have this relation. So this determinant comes from this Jacobian factor for the integral. Then all this is given by lambda is include both coupling functions and disorder potentials. Then from this equation, we find this algae flow equation for the distribution function. It is not possible to solve this nonlinear partial differential equation in a general situation, where there exist large flows at intermediate and scales. On the other hand, we may find a general behavior in the vicinity near the fixed point and inserting it into the large flow equation of the distribution function. We obtain on the other hand, we may find a general behavior in the vicinity of a fixed point by vanishing algebra functions. Linearizing the algebra function here. So I will explain it. So linearizing beta function, we obtain the critical exponent here. Just plug in the previous equation with this one. You can solve. So this linear diagonalized blah blah blah. Basically, you will have power distribution behavior. That's the key result. So here, the power exponent is given by critical exponent of unknown scaling dimensions of coupling functions real to the fixed point. In this respect, we identify this novel disordered critical phase with an infinite randomness fixed point, as discussed in the introduction. We may apply this framework into a one-dimensional lattice system where the RG transformation is given by pattern of block spin transformation. So for the time being, we consider a one-dimensional lattice polynomial model without their interactions. Here, T is Hopping integral, and U is chemical potential, and V is random potential. This is given by Poisson at UV. If you integrate, if you separate even and other site degree of freedom and integrate all the even site dynamical fields, and their corner fluctuations renormalize the dynamics at other site degree of freedom, so like this one. So chemical potential is renormalized like this one, and Hopping integral also renormalized like this one, and like this one. This is the effective potential after alpha integral. This is given by some non-interacting Fermi model. So this is the algebra procedure. So we have to reformulate this in terms of renormalized one, like this one. So using this relation, we obtain like this one. So here the relation is like this one. Here like this one. If we repeat these algebra transformations, we obtain the following expression, where the superscript k indicates the case iteration of the pattern block spin transformation. So from k minus 1 to k by this one, like this one. So this final renormalized ones, like this one. This is extra dimension. So k minus 1, like this one. So renormalized one. Thank you very much. You can make.
Thank you, Dr. Kim, for your interesting
continuum representation for this discrete expression for the RG transformation, where
effects of RG flow to overcome the problems of UV and IR divergences. Okay, any question? Maybe one question. Let me take this opportunity to ask our audience, please, if you have any question, you can use the chat box, and then maybe the speaker can answer your question in due time. Okay, I think there is no any question. And
Thank you very much, and I
again
appreciate
our,
this nice workshop. Thank you.
Speaker, Dr. Kim, thank you for your time and for your very nice